Hi everyone, so this is the second episode of this series of mindmap. So in the previous one, we have gone through the basic part of mechanics, topic A1, 2, 3, and D1. And so in this episode, we'll then now going through to the electricity and magnetism part. And so if you haven't got the first one, I think it will be best if you can go through that one first so that you understand what we are doing. And also in this episode, we have some connection going back to the concepts that we have covered in the first one. So without further ado, let's start with electricity. So same way, I will be using the stem to indicate that we have gone through those things. And again, this should be something that you should do when you are making use of this mind map. All the comments are welcome, so if you have anything that you can think of that can improve this mind map, you can write it down and then let me know in the comment section later on. So electricity, I start usually teaching with B5, which is more like a macroscopic, something that you probably have seen it in middle school already, concerning about circuit before we go to static charges later on. Of course, electricity is very closely related to magnetism. If some of you have basically done this chapter, you know about it, and maybe even more, you heard about something called Maxwell equations. You know that they basically are intertwined together. Anyway, so coming back to circuit here, we first have, of course, a lot of different circuit components. So in the data booklet, you find all those symbols. And the very fundamental thing that we have is how we can characterize them. Okay, very similar to motion, we characterize them with displacement, velocity, and acceleration. So here we've got voltage, which is also called potential difference, current, and also resistance. For each of them, you can see they have their own equation for the definition. So this is for V, I, and R. Okay, for R we have a name that associate with it called the Ohm's law, but it's not really the way that we define resistance, but Ohm's law is more talking about whether or not the component is behaving proportion with V and I in proportion. So that's how we come up with the word ohmic and non-ohmic, because it's called Ohm's law, right? Ohmic and non-ohmic behavior. And so the reason why we have resistance is because the mobile electron are colliding with the atom. So the less collision that they may have, then less likely they can have resistance and less energy lost due to this interaction. So we also have another equation describing how the resistivity, how the cross-sectional area, and also the length will affect the resistance. But don't forget, this is more like the physical dimension. We also have another very key factor, which is the temperature, which could affect the resistance. So that would decide whether or not it's ohmic or non-ohmic. And of course, there are some other things like whether or not they're semiconductor, etc. So in the different component that we may have seen, the very simple one is called the fixed resistor. You may have a wired called the filament. Okay, usually the one that in the light bulb, for example, and then their behavior, they are non-ohmic, and their behavior is when they have higher temperature, the resistance will be higher. We also have some other component called variable resistor. So one of them is just a physical variable resistor. Some people call them rheostat or potentiometer. Then when it's basically sometimes you have a knob, you have a slider. Okay, they come with different form, but basically what they do is they can change the resistance according to these change manually. And the mechanism is simply due to the same way that how we have this equation earlier, okay, that the longer the length, the bigger the resistance. Okay, so how much resistive wire that you have gone through. The other two rather special component is called thermistor and light dependent resistor, LDR. And apparently one work with the temperature, one work with the light intensity. And when these things go higher, then the resistance will go lower. So the easier way that you can memorize it is the filament go high temperature, high resistance, thermistor is the opposite, and then the light dependent resistor is the same direction as the thermometer does. So going back a little bit, we actually should talk about the idea of voltage. So first of all, in the syllabus point, just to make sure you have it, you have to know that the cells is a source. Okay, chemical or solar cells is the one that provide you the voltage, which I believe everyone should know. And when we look at the definition of voltage, okay, it's work done per charge. It can be measured by voltmeter. Current is measured by ammeter, and then they have their own way to arrange in the circuit. And then if they are ideal, then voltmeter will be of infinite resistance, ammeter should be of literally zero resistance. And if you want to know why, then you might have to refer to the video that I made earlier. One thing special about voltage is that normally when we substitute the numbers into this equation, you will get the energy in joule divided by the charge quantity in coulomb, and then get the voltage in volt. But then there are some topics, okay, or even in this topic, you have to learn that how to convert between joule to another energy unit called EV. So this is the way that you should do it, and you can find this number, which is elementary charge, in the data booklet. Now going a bit further, between the V and I, you can then work it out, because as you can see, if you just try to derive them, you can figure out the power, which is energy over time, as you can sort of cancel out the Q on both sides, and then W divide T, and therefore you get the power. So that's how you get I times V, and then you can use the Ohm's law to make the other two variants of it. Now I think we are pretty good with this area, okay, except now we go a little bit further, that the circuit can be arranged in series and parallel, and so these are the behavior that they may have for a series circuit and parallel circuit. Apparently some circuit may be quite complicated, where locally they are series at a certain point, and then locally they are parallel, so it's a mixture of the both. You may have to look at them locally one by one. So this is a relationship. Series circuits, they have the currents being the same, but then the voltage all have to add up together. And then parallel circuits, all the currents have to add together to be the main branch, but then the voltage would then be equal for each branch. So you can see it's basically the other way around for series and parallel. And then there's a way you can derive them. So then using the idea of voltage, you can derive the expression of equivalent resistance. So this whole thing is provided in the data booklet. Now, because of this very interesting interaction, then we can have something called the potential divider. This simply is usually in the practical working with the rheostat, okay, the potentiometer we just mentioned, and then how you can accurately allocate the potential. That's why it's called potential divider into a certain component. So that's because when you put them in series, okay, then they will follow this series circuit relationship, because like we said earlier, that the total voltage is the sum of the smaller part voltage. So by adjusting the ratio between the resistance, then you can have this result. Okay, so again, this is called potential divider. Usually my student may not fully understand very well, but then yeah, you might have to go back and take a look again on those content. The other thing that we may find is something called internal resistance. I thought of connecting it with the cell, but it's a bit too far and I think it's too obvious, so I didn't make the link. Internal resistance is talking about when we learned at the beginning, we thought that the cell is ideal, but in fact they are made of certain component and they must have certain resistance. So the small r here denoted the internal resistance. The epsilon here is the EMF. So they also have a relationship when you plot them onto a graph. If you perform an experiment, try to plot data on the V, this V is talking about the actual components. For example, you have a light bulb. Okay, it must have a certain voltage when you have having different currents flowing through it. So eventually you'll be able to plot this graph and the gradient is negative small r, which means that to find the internal resistance, you can just find this and then take away the negative. While the y-intercept would be the EMF. Okay, so this is a very core essential idea that you must have. All right, I think we are good to go on to the charges. Okay, so we have pretty much done with the circuit. Now going to the static charges. Okay, so the first thing that we have to we clearly will find out and know is there are two kinds, positive, negative. Depending on light charge or opposite charge, they would attract and repel. We also find that charge conserve. Okay, so you cannot suddenly take away the charge out of nowhere or suddenly vanish. Okay, get the charge vanish. So there are different ways that the charge can be transferred. And then in the booklet, we have mentioned that it can be done by conduction. So maybe two metal sphere, okay, that simply they will just conduct and equalize accordingly depending on their density. And then it can be done by friction. Okay, in fact the word electron is from I think I can't remember it's Greek or Latin. Okay, the word amber, because people in the past use amber to rub the cloth, and then that how by friction they come up with those charges. And lastly is the induction. And then for the induction, there's a video to talk about the whole steps, how you should put maybe a charge rod into something, and then push the charges to one side, and then you have to earth it, and then you take away, etc. So for the whole process, I'm not going to repeat here, but one key idea is the idea of earthing. And so if you want to recall the detailed steps again refer to the older video. Now let's go on to talk more about how the forces between the static charges can be described. So there's a law called Coulomb's force, okay, that you can find here. It's very similar to gravitational force, and therefore here I also put it down the definition, the word definition of it is very similar to the one we have in gravitation. So as you can see is something called electric force is directly proportional to the product of 2 point charges and inversely proportional to the square of the distance between centers. So basically is the same. Now because we have a force, we can always describe the electric field strength as mentioned in the previous video. For point charges, okay, then we can make use of this equation, force per charge for Coulomb charge. And so here is a word definition. Again, it's very similar to gravitational field strength, except that this time, pay attention, we must emphasize it is per unit positive charge, okay, because the direction of the E field is pointing to you the direction that if you put a positive charge there, the force that it will experience, not the negative charge. Negative charge will go the opposite direction. So when you talk about the definition, you must put the word positive, okay, for the positive charge. Now when we put these two equations together, then we can derive this equation. Again, it's very similar to the one you have in gravitation. Going on, when we look at the electric field pattern, there are actually more than just this one I show you, but basically it's positive and negative. We talked about it in the last episode, and then you can find many more from your lesson and maybe on the internet, or even in the simulator you can try it out. Okay, so that's electric field pattern. One thing again you may pay attention is the electric field strength, okay, which is denoted by the big E, inside a conducting sphere is 0. Okay, so imagine you have a sphere, inside the E field is 0. The idea is very simple. You don't have to memorize it. If you understand that if you have charge on this conducting sphere, they must have distributed evenly because they will repel each other, right? And in that state, there must be no more movement and forces because it's already in equilibrium. That's why they are not moving anymore. So that's why the E must be 0 if the force is 0. Now going on, we also have another electric field pattern, okay, between the two parallel plates from positive to negative. Okay, so inside as you can see, the density is equal. So as we mentioned, this field strength is related to the density of the field lines, and therefore the field strength is a constant. Okay, inside this parallel plate. On the side, there is something called the edge effect. Okay, as you can see, it gets weaker because apparently it's on the side. Okay, so there is of course a limit, and from the pattern you can also see that it's less dense. Okay, and that's showing you that is weaker on the side. For the electric field strength, okay, just now we have remember the F over Q. This one works for charges, but then if you are looking at parallel plate, it doesn't work. Okay, so what you can do is you can have an equation like this one, E equals to V over D, but again, pay attention that this is for parallel plate only. So you cannot take this equation to point charges or other places. Okay, this is a very specific equation that you can use for parallel plate. All right, talking about charges, I think we are pretty much done here. Before we go on to moving charges, okay, there's one thing that I guess we have to talk about here. Okay, I forgot this, there's a branch here. So for the static charges, okay, one thing that is new to this syllabus, okay, which you find an older past paper, you can't find anything about this. It's called the Millikan oil drop experiment. Okay, so basically the aim is to find how we can quantify the number, okay, estimate the number of elementary charge. So that's basically it. And one important finding is that it provides evidence that the electric charge is quantized. That means it's of a discrete number. So it's different from like for example, if you measure your mass, in fact it should be a continuous number. Okay, and then this one is found to be quantized. So a very specific number that we can calculate. So it's done by observing the stationary oil drop when there are two forces. Okay, in a simplistic way, when we see there are two forces. One is the electric force, because the oil drop are charged somehow, and then they have certain mass, and therefore they have gravitational force pointing down. So because gravitational force must be pointing down, and therefore the electric force must be pointing up, and then we can then put the equation like this: electric force equal to gravitational force when they are stationary. So this may be the equation that you can use directly, but sometimes they may come up with a parallel plate scenario with you, so maybe more information, and therefore, okay, you may come back to just now this equation and put these two equations together, and then you can derive this equation. Pay attention that the parallel plate, this one, okay, electric field strength is provided, but then these two are not provided. So you really have to understand and then be able to derive it yourself. Your syllabus is not making it very clear, so there's a chance where the oil drop actually are modeled with more forces. Okay, so that's why I just now said it's a more simplistic model. If the question or the scenario is described with more information, in fact you can consider the buoyancy force and also the viscous drag force. So if you remember, these are the things that we learn in the mechanics. Okay, and that's why I put a really long linkage, okay, back to here. Okay, these are the forces that we talked about earlier. Okay, so let me see if there's anything that we missed, and that's the whole point of the mind map. So I believed, okay, here for electric force, okay, when there's a charge enter the uniform electric field, okay, you need to describe the motion of it. So here is a very nice diagram, shows that the trajectory. In fact, the idea is very similar to a projectile motion with gravitational field. So if you throw a basketball, that's the parabolic trajectory that you have, and for charges it's exactly the same. The only thing is that it depending on whether they are positive charge, negative charge, and also direction of the plate, then they will go in a different way. So it's like you can basically flip the paper around, okay, for the cases down below here, and then you use the same idea, as in they experience the same acceleration, okay, I should say the constant acceleration, just like how you describe a basketball is experiencing the same gravitational acceleration, 9.81 on Earth, for example. Okay, so the whole trajectory can be described using the same equation you have in kinematics. The last thing before we go on to moving charge is going back to this equation. So in fact, the K is a constant normally, and then you can see in your data booklet, it said that is equal to 1/4 pi epsilon log, and that's symbol is representing the permittivity of the medium. Because when I look at the syllabus, it said that it may provide you a range of permittivity. So you just have to be flexible and be aware of this is permittivity, and then what you may have to do is just to change to another permittivity. So normally you might be just using air or vacuum, but if it is in other medium, then you just have to substitute that number instead. So it's probably provided in the question. You are not, of course, not expected to memorize any numbers. Now let's go to the moving charge. Okay, I know here we've got the yellow part, okay, the HL part, but let's finish the SL part first. So the moving charge is in the B field. When they are in the B field, they will experience the magnetic force, and this is how we also make DC motor, which is very important nowadays. When we talk about magnetic force, there are two kinds scenario usually. One is when you have charge, okay, so therefore you use this equation. Very likely you see it, and then it's something to do with the circular motion, because this magnetic force is to become the centripetal force in the circular motion. In the circular motion, the kinetic energy of the charged particles stay constant, because as you can see, the force and the velocity direction are perpendicular to each other, and so using the work done equation, you should know that it stays constant simply. I couldn't make a link from here to circular motion, but on your PDF, if you try to click it, you'll be able to go back, okay, to circular motion. Okay, so this is like a portal. Okay, you teleport from there going back, okay, to the first episode. So I hope that is something useful, okay, and then sensible, that keeping our map still clean. Now going forward, of course we can also describe the motion, okay, of the particle in the magnetic field either way, and then for strict currents carrying wire, because if you think about a wire, okay, inside there are electron moving, and basically the current itself is the movement of electron. Actually, I think I make it here also, yeah, at the very beginning. The moving charge is pretty much a form of current itself, okay, and so that's an idea that you also need to have. So using this idea, and then we can actually derive this equation, okay, BIL, and then using this equation further, we can also derive when two straight wire having currents going through are parallel. You can describe the force between them. However, the derivation is a bit ill with our syllabus, because you only can derive it if you know how to describe and characterize the B field between the straight from the straight wire. So if you're interested, you can try derive it. You can find this equation very easily online, and it's quite fun. Okay, but if you don't, it's okay as well. As you can see, I denoted here as gray color. It means that it's off syllabus. Anyway, the key point of using this equation, okay, the forces between the two straight wire, is that you can quantify this way. The other thing that you should pay attention is, if the current is the same direction, the force is in the attracting direction, while if they go opposite, so say one go up, one go down, then they will repel to each other in terms of the force. Last but not least, you also have to pay attention and recall that the magnitude of the force must be the same. Okay, even though maybe the current one is higher than the other one, because of Newton's third law, then the force magnitude must be the same. Now going a little bit more, because we now talk about how the charge can move in E field and B field, and so in fact they can put these things together. Okay, this is explicitly mentioned in the syllabus that you may have an E field and B field. It's just that they go in a perpendicular direction, and so you also have to describe the motion. So maybe it can be adjusted in a way that the charge can go straight by carefully adjust the E field and B field in a certain way. And using this, in fact, the scientists practically can measure the charge to mass ratio, and by measuring and investigating the path. So there's an equation. Okay, again, I'm not really sure whether or not it will be asked, but then, sorry, this is derived. It may be required, okay, step by step in maybe the exam situation, guiding you to this equation. But certainly this could be something you will encounter. And so if you're not sure how we can derive this equation, then try to do it yourself. Okay, try to put yourself into a test. But basically, you are just using all the knowledge that you have here. Now let's go back something easier. So in terms of the two magnetic forces, no matter it's charged or on the wired, the direction, okay, although this is equation, okay, they can find you the magnitude, but then in terms of direction, you have to use flaming left-hand rule. And again, I'm sure many of you are fairly familiar with this already. Alright, so let me see if anything green left. Okay, I think it's just this part. So now we go to magnetism. Okay, sorry, I'll go back to the electricity part later on for HL. So for currents, okay, as you can see, there's a branch here that when you have currents, then you have magnetic field. In fact, this is how we talk about the two parallel wired can interact with each other, because each of them will induce a magnetic field. Okay, and the way that we can determine the direction is by using right hand grip rule. So you can grip this way. Okay, for strict wire, for solenoid, you can also use a grip rule to find the B field as well. So yeah, very essential. So finding out the magnetic field, and we can have the magnetic field pattern. It go from north to south. Okay, and so again, going back to the previous chapter, we briefly touch base on the gravitational one. Now you know the other two. Okay, the gravitational, yes, of course, electric and also magnetic. So magnetic field strength, unit is Tesla. The symbol is denoted by B. So this is how much the SL need to know. Alright, so HL students, our party start now. Okay, going back to electrical. So electric force we talked about earlier, okay, K, Q1, Q2 over R square. Okay, so it's very similar to gravitational. If you try to look at how we define work done, we can do a calculus with that by looking at how the potential energy at infinity is 0 again. You can derive the electrical potential energy. You can find the expression very similar again to the gravitational one. Here is the word definition again. It's very similar, except that you must emphasize it's a positive charge. Okay, and so again it's energy, and therefore it's scalar. You can just add them together in a way, okay, so then you don't have to care about the direction. You don't have to take trigonometry for potential energy, in fact potential as well. So again, very similar to gravitation, you have electrical potential by taking away charge, and so you have this equation. You can have a word definition as well. The potential energy and potential is talking about at that point. So if you're talking about the change of them, okay, that will be the work done. So that's why we have an equation like this. The change of potential multiplied with the charge is the work done required. Now we also talk about how the potential is changing over the distance. So same as gravitational, we have an equation like this one, okay, delta V over delta R. So the equation, okay, that or the technique like this one, okay, last time we talked about in gravitation, will also apply, okay, just so you know. And for the potential just now, okay, we also have equal potential surfaces in electrical. So these are the diagram. Okay, you can find many more online. And then the key idea is the electrical field lines and equal potential line are perpendicular to each other. So same as what we said in gravitation. Here I got so-called a hyperlink. You can go back to the gravitational one. Okay, so you can see, okay, to see anything that's related to these ideas. All right, so I think on this side we are pretty much done. Yes, pretty much done. So let's go back to magnetic. Now in D4, okay, so we have talked about magnetic field strength before that, and now the magnetic flux. Okay, fine. So this is the equation. And so you can see the area will make an effect, and also the angle, okay, will make an effect. And then if you have more than one coil, okay, for example, then you can talk about the magnetic flux linkage by multiplying n with it. And as long as you can find the rate change of it, then you can find the induced EMF. Okay, this basically is the Faraday's law. Okay, if you have change, I'll say again, if you have change of magnetic flux linkage, you have the induced EMF. We can find the magnetic through that. Okay, and this is the first thing that we have, induced EMF, but only if the circuit is complete, then you can have induced current. Okay, so some students, as a misconception, think that there's always induced current. Okay, but it's not really true. Okay, you always have induced EMF if you have a change of magnetic flux linkage, but then whether or not you can have current, depending it can flow, right? So whether or not the circuit is complete. So for finding out the induced current, there are two ways. One is the Fleming right-hand rule, okay, which you find very useful in generator, for example. The other way you can use to find the direction is called the Lenz's law. This is the word definition of Lenz's law, which I think is important that you should memorize it. The idea of why Lenz's law is a thing is actually in order to obey, guess what? The energy conservation. Okay, so yeah, I really want to make a link, so I don't care how long it is. Okay, we have to go back to energy conservation. So the reason why you have these currents, okay, is because to conserve the energy. All right, so that's why when we have seen some scenario talking about the eddy current, okay, you'll find out maybe a magnet dropping through a metal tube, it will go slower. So the kinetic energy or gravitational potential energy change into electrical energy in the current. The other scenario that you may encounter, explicitly mentioned by the syllabus, is a magnet oscillating on a spring. So we haven't get to that topic yet, but later on in wave, there's something called simple harmonic motion. Okay, that say going up and down or left and right. Okay, let's say going up and down. Okay, and so about the conducting coil. So perhaps, okay, it will induce the energy in it, and so the amplitude of the simple harmonic motion could decrease. So it become not a simple harmonic motion anymore. It become a damped motion, which all HR students you will have to get to learn in the later topics. Now there is something sketchy here that you may overlook. Okay, in the syllabus there's something called the self-induction, and then it didn't say in the syllabus point, but then it said in the guidance. So it says you only need to know qualitatively. And so if you try to search for its definition, okay, it's basically this. This is basically talking about when the current is changing, and because the current is changing, the B field is also changing. Remember, current will make induce B field, okay? And so this B field coming back to itself will induce an EMF, okay, in the same coil as you can see here. And so this is called self-induction, okay? So you just have to know the qualitative idea. If you're not so sure, then put yourself some time, okay, to try look at the sources in the textbook or online. There's something very similar called back EMF, okay, which I also put here. I find it's quite interesting. The idea is also similar, that when the coil started to move, okay, there's a change in the EMF and also the movement itself. So when they move through the magnetic field, it will then induce the EMF in a way that it is opposite to the one that is being applied. So that's why it's called back EMF. So that means in reality, because of this movement, the increase of EMF takes longer time, okay, than you might expect. So it's not increasing instantly. I putting it here is because I would say, I mean, this is basically using the same idea that all you have learned, okay, from within the syllabus. So they might still ask you, give you a scenario like this and ask you why, okay. I think in the old syllabus I've seen it before in one question, I think out of the many years, okay, I've seen it once or twice, okay. But again, back EMF wasn't even written at all in the syllabus, so who knows, okay. I think again it's more about all these fundamental theory, then you should be able to apply it. Alright, so those may be a little bit too hard to accept, but now we go back to something that's probably easier for you. So Faraday's law, okay, because we haven't checked this part yet. Faraday's law, this is the word definition, this is how the equation look like, you have it on the data booklet, and usually, okay, you'll be focusing on having this to describe the AC generator. Because of the rotation of the generator, then the magnetic flux linkage will be described like this. I put a cosine here, but it depending on the configuration. So it could be a sine, it could be having any sort of phase that you have. That's okay. Okay, so but using this by finding the time derivative of it, okay, because of the Faraday's law, okay, we have to divide the t, right? So the time derivative of this you can find will be this one. A bit of calculus, but I think it's very essential that you try to derive it yourself. And then by considering the power equation, okay, just simply from the power equals to IV, okay, this equation, but here we will be using V squared over R because it's easier to interpret. And so we can find the power expression in terms of omega, okay, and other things as well, of course. So the key conclusion is that if the frequency increase, okay, then say frequency increase by 3 times, then the EMF will also increase by 3 times. But then for power, it will be increased by 9 times because it's a square, okay, as you can see, omega NBA bracket square. And so this basically determines the amplitude. I mean, it's a sine square function, okay, but then the amplitude is confined by this whole thing, okay, minus R, of course. And so power proportional to omega square, and omega is 2 pi f, and therefore power is also proportional to f square. Qualitatively, you also need to know how at different configuration of the coil, when it is parallel or horizontal, parallel or perpendicular to the B field, how the voltage induced rate it will be. And so, for example, if you look at this vertical one, because it is now going horizontal, it's at the vertical already. So now the next movement is going back to horizontal. As you can see, the velocity is perpendicular, sorry, it's not, it's parallel, okay, it's parallel to the B field, okay, and therefore it doesn't really cut the B field, and therefore the induced EMF is at 0. While when it's at horizontal, okay, because it's about to turn back to vertical, it is the velocity being perpendicular to the B field, and therefore the rate will be the greatest, okay, although it's negative, that's because of the direction of the current, but the magnitude is of greatest. So that's why you see, okay, here and here, okay, they are both maximum, while whenever it's vertical, the EMF will be 0. So you need to be able to visualize the idea like this. Alright, so last thing I think here we haven't got is simply using Faraday's law. It may not be as complicated as an AC generator. It could be just simply having maybe a metal rail with B field shooting within the area, and then having a straight conductor that's moving, you know, on the rail, okay, perpendicular to the B field. And so from that we could describe that, and then we can also talk about how the area, okay, is being changed when the rod is moving, okay, based on its velocity. And so we can find the induced EMF expression in this way also. Alright, so I think that is all. Yeah, I see all the thumbs up here. So yeah, again, if you have anything that you find I missed, anything you can suggest, I can rearrange it so that it looks better, please let me know in the comment. If you like this series, let me know so that I can continue to make the rest. I'll see you again. Bye.